I've got a triple integral up, oops, I wanted that to be a z. I've got a triple integral up here on the board, and it's already set up. And very often with these problems, the hardest part is figuring out the limits of integration. So at first glance, you might see this and say, oh good, the hard part is done. I don't have to figure out my limits of integration. And then you look at what they are. And they're these square roots of subtraction problems involving variables squared. And I just don't really feel like working with those in integrating. Okay? And anytime I do see square roots, where I'm subtracting variables squared, I'm thinking round stuff. I'm thinking spheres, I'm thinking circles. So I'm thinking we probably want to switch this to spherical coordinates if we can. Okay. So that means we're going to have to visualize what the region is so that we can describe it in cylindrical coordinates. So if I look at, these are my z values. Z goes from 0, got it. That's the xy plane. To the top surface is z equals the square root of 4 minus x squared minus y squared. You might recognize, and if you do, fabulous, that's the top half of the sphere of radius 2. If you didn't recognize it, here's how we get there. Square both sides, recognizing that since z was defined to be a principal square root, it's non-negative. But now when I add over the x squared and the y squared, that's looking very familiar. X squared plus y squared plus z squared equals 4. That is, with z being non-negative, that is the top half of the sphere of radius 2. Excellent. Okay. Now, these together describe the region I'm going to have in the xy plane. So, x is just going from 0 to 2. So the y-axis and the vertical line x equals 2 are my left and right boundaries. Y is going from 0, that's just the x-axis here, to the square root of 4 minus x squared. Now again, if you recognize that that's the top half of a circle of radius 2, fabulous. If not, here's how we get there. Y squared is 4 minus x squared, but y is bigger than or equal to 0 because it was defined to be that square root, and square roots or principal square roots are not negative. X squared plus y squared equals 4. Okay. So this curve would be the top half of a circle of radius 2. I just want the part between where x is 0 and where x is 2, so we're looking at this quarter disk. Now if I put all of the pieces together, we're looking at this quarter disk going from here to the top part of the sphere of radius 2. So we're actually just looking at an eighth of a sphere, the portion of the sphere of radius 2 that lies in the first octant. So with that, let's set this up in cylindrical coordinates. Going from bottom to top, we're going from 0 to, we said the top half was z is equal to this square root. In cylindrical coordinates, that just becomes the square root of 4 minus r squared. Now, if you're doing your integration so that you're integrating with respect to z first here, and now I've committed to I'm going to integrate with respect to z first over here, it's a direct lineup. I'm literally just translating these functions into their corresponding formulas in cylindrical coordinates. Not so with x and y, because I'm switching x and y together to r and theta. It's not like x becomes r and y becomes theta. xy becomes r theta. But we figured out that we're working over this quarter disk. Over that quarter disk, r is going to vary from 0 to 2. And theta's just going to go from 0 to pi over 2, so that we just get that quarter of the disk. Okay. We were integrating z, and don't forget, all of this was essentially just dv. dv becomes r dz dr d theta. Don't need all that space. So my integrand actually becomes z times r. So integral from 0 to pi over 2, integral from 0 to 2. Antiderivative of this with respect to z is going to be z squared over 2 times r. That's evaluated between root 4 minus r squared and 0. And then we've got dr d theta. So that's the integral from 0 to pi over 2, integral from 0 to 2. When I plug this in and square it, I just get 4 minus r squared over 2 times r, minus when I plug in 0 for z, I do just get 0. So we still have to integrate that dr d theta. I'm just going to factor out that 2 on the bottom. Integral from 0 to pi halves, integral from 0 to 2, and let's distribute that r. So it's 4r minus r cubed dr d theta. All right, so that's 1/2 integral from 0 to pi over 2. Antiderivative here is just going to become 2r squared, because it's 4r squared over 2, minus r to the 4th over 4. That's all evaluated between 2 and 0. And then we'll still need to integrate that with respect to theta. Let me just clear some space, and we'll finish this up. Okay, so we've got 1/2 integral from 0 to pi over 2 of, let's see, when I plug in 2, I'm going to get 2 times 4 is 8, minus 2 to the 4th is going to be 16, divided by 4 is 4, minus, when I plug in 0, I do just get 0. And we've got to integrate that with respect to theta. So this is just 4, so we're integrating a constant. So it's the integral of 1/2, 0 to pi over, 1/2. The integral from 0 to pi over 2 of 4 d theta. When I integrate that constant, I'm just going to get that constant times the length of the interval from 0 to 2 pi. So that's 4 pi over 4. That's just pi. Okay, I have fewer videos for this section than I do for most sections. That's because we're going to revisit cylindrical coordinates at the end of the next section, where we're learning another way of describing points in 3 space called spherical coordinates. Once we've learned that, we're going to spend some time just setting up various integrals in all 3 coordinate systems so that you can start developing a sense of when which coordinate system is going to be the most strategic choice. Okay, so we've covered everything you need to know in order to do the homework on cylindrical coordinates, but we will be doing more of this together in the videos as we finish up the next section, which is spherical coordinates.